I'm Jono, like technical lead from Cisco. I'm working in Kubeflow related.
Okay, so I'll speak to English now. So today's agenda, we're going to introduce hyperparameter tuning, and we'll be briefly covering what it is and why it's hard. And we'll go into our main topic, which is Kubeflow and Catip, and we'll see how these systems will help us do hyperparameter tuning. And we'll give a brief talk about the system architecture and the workflows. And we'll also show a quick demo of our system. And then we'll go into neural architecture search, which is a new area of research and implementation that Catip has done. And finally, we'll go into some future work. So what is hyperparameter tuning? So let's start with an example. Okay, suppose that we're doing this, this is a very basic machine learning program for recognizing digits. Right? So on the right-hand side, you can see some training code, and in fact, right on the bottom there, you can see that this is where we're starting to fit a model. Right? So hyperparameters are the parameters that you set before the training process begins. So if you look at this list, we have the network, batch size, the number of epochs, the learning rate, and so on. So these are the parameters that are that governing the training process. They're external to the training model. Right. This is in contrast to model parameters, which is learned by your training. So hyperparameters, configuration variables that are external to the model, and they're set before the training begins. And so setting the right parameters can really significantly improve your model performance. But it's only if you don't do it correctly, which can be very difficult. So hyperparameter tuning is the process of finding optimal values for hyperparameters such that your objective function, in the previous case, that is our function to predict digits, handwritten digits. You want to maximize the prediction accuracy. Okay. So why is that hard? First of all, if you increase your number of hyperparameters and your hyperparameter ranges, the search space becomes exponentially large. Right? So in previous slides, we've seen about 6 or 7 parameters. So imagine if you have a more complicated model, right? And your space is just going to grow. So tuning by hand is really inefficient and is very prone to errors. And you want to, in order to really track your performance from one configuration to another, you want to track metrics across multiple jobs. So that means you have to have some kind of a data storage, some kind of a visualization interface to see what your experimentation has done. Maybe you want to anchor on some particular value for one parameter, like the batch size, and you see what changes when you adjust the learning rate, right? So you need to be able to track metrics. And also you need to be able to manage resources and infrastructure. So training jobs, sometimes they require additional, maybe additional hardware, some computing resources. So you want to be able to allocate and to provision and to clean up the resources. And finally, there's a lot of different frameworks and algorithms to support. For example, just from training, the example that we've seen is for MXNet. But you can have a TensorFlow or PyTorch model and algorithms that could be grid search or a random search or Bayesian optimization and so on. Right? So there are lots of different, a variety of similar problems. So how does Kubernetes help us? So first of all, Kubernetes makes it really easy for you to build microservices. So microservices are self-contained and lightweight services that do one thing really well. And Kubernetes also makes containerization easy with Docker. So the good thing is that really applies to our model of parallel training jobs, right? Because jobs, we can containerize them, and this makes them very easily scalable. And this also helps our system build up resilience, right? Because Kubernetes provides auto healing and recovery options. So is meaning that the failures of a particular training container it won't affect the whole system, and the system can actually automatically bring it back up. Okay. This also helps us with our problem of multiple frameworks and different algorithms to support, because we could create this generic interface that's us interacting with the algorithms as microservices. So we'll go into more details about that in a bit. And Kubernetes is also pretty good at describing the desired state. Right? So we call those declarative APIs versus imperative. Right? So this is remember we talked about we want to manage resources. Right? So this makes managing resources very easy, because all you need to do is describe the desired state instead of having to write complicated instructions on what you want to provision. Kubernetes has a very flexible API, meaning that we can extend the core API with custom resource definitions. So this allows us to interact with the objects using the standard REST APIs and tools like kubectl. And finally, Kubernetes is very portable. So in production environments, we often have to deal with different environments, like if you're doing local development versus doing on-premise hosting or even moved in cloud. Right? Kubernetes has various options, but if you're built on top of Kubernetes, your application should run everywhere where your Kubernetes cluster is deployed. So a little bit about Kubeflow. So Kubeflow is Kubernetes native machine learning platform for developing, orchestrating, deploying, and running scalable end-to-end machine learning workloads. So that's quite a mouthful, right? So if you look at this diagram, and it's not to scale, but a lot of problems with building machine learning in production deals with the things in the blue boxes, right? So monitoring, service infrastructure, analysis, processing management tools, and so on. And your machine learning core logic might be just only a small part of it. So Kubeflow wants to make building all the other stuff easier, so you can concentrate on the core machine learning logic. Okay. And so right now I'll turn over to John, who will go over us, introduce us to Katib.
Hi everyone. So let's talk about Katib. So Katib is the hyperparameter tuning component in Kubeflow. It is completely Kubernetes native, so that means you could install it even without Kubeflow. But then if you want to use features of Kubeflow, like the distributed training operators, then it is advised to use within the Kubeflow ecosystem. So it is inspired from the Google Visia project. You would have read the paper. It's a black box tuner. You could, the link is given in the below comment, you could read that. It's fully open source, and it is framework agnostic, so which means you could use your programs based on your choice. It could be written in TensorFlow, PyTorch, MXNet. You could just provide the images and it should start running. It has a customizable algorithm backend. By default, it provides random search, grid search based in optimization hyperparameter. User could plug in any algorithms based on their environment, and you don't need to even restart the components. It would be started as a separate microservice, and it should, without even restarting the component, it should start running. So let's talk about the concepts. The first concept is experiment. So it's an end-to-end process for hyperparameter optimization. So for example, take example of a digits recognition model. So you have to find the best hyperparameters for that. So that's the experiment. The users provide experiment config and submit to Katib. So it has different sections. The important sections are, one is objective, which is what we are trying to optimize. For example, for your model, you want to optimize accuracy, and what you want to achieve is 99%. So the objective metric name is accuracy, and the value is 99%. The second is the search space, which is the constraints for configurations. So you could set limits for your parameters, say the maximum or the minimum, or if it is categorically, you could set the list of options that are valid for a particular option. And the last one is the search algorithm, which is how you find the optimal configurations. So in the last slide, as we said, you could use the default ones or the ones which is added by the user. So like any other resource in Kubernetes, Experiment is also a resource. To be specific, it's a custom resource. So you could use all the standard APIs to basically create and delete the Experiment resource. You could use kubectl like any other resource in Kubernetes, and the state is stored in Kubernetes database. And the lifecycle is managed by the Kubernetes controller pattern. The second one is suggestion. So once user submits the experiment config through Kubernetes API, the experiment controller picks it up and contacts the right suggestion service. So suggestion is one proposed solution to optimization problem. So you have set the search space, and the suggestion is provided based on the settings given by the user, which is one proposed solution which is given by the suggestion service. So each suggestions algorithm is a standalone microservice. So which means you could add that during the runtime, and it should not affect the already running experiment. And it allows user to create customized suggestion algorithms. And the third one is the trial. So once suggestions are provided by the suggestion service, the trials are created by the experiment controller. So trial is one iteration of the optimization process. So which means once you get the parameter assignments or the suggestion, there's a worker process which actually starts running it and emits out the observation metrics. So similar to trial, similar to experiment, trial is also a custom resource, and the experiment controller is the one which is spawning and managing the trials. And depending on the trial kind, you can have the distributed job for it. So this is a basic workflow of the hyperparameter tuning. So as I said earlier, this is the one optimization loop, and this loop continues till one of these conditions are met. So either the objective value is reached, for example, once your accuracy has reached 99%, or if the budget has exhausted. So you could also set that my maximum number of trials to be run by this experiment is X. So once X is reached, or when your objective is met, the optimization loop ends. Till that time, the suggestions are created, and for each suggestion, trials are run, and the metrics are emitted. And these metrics are collected, and new suggestions are created. So this is a system architecture. So the user submits experiment, and experiment controller is the Kubernetes custom controller. It picks it up and talks to the right suggestion through Captive Manager. So algorithm related settings would have been given in the experiment. And once the experiment controller gets suggestions, it creates trials. The trial controller again picks it up and starts executing trials and starts emitting metrics. The metric collector is a separate process, which again, during the lifetime of trial, it collects the metrics and writes to the data store. And this would be again used by the suggestions for the future suggestions, and that loop continues. Yeah. Due to network, we are not showing it live, but again, we have a Captive UI, which actually provides much of the features in the as a user interface. But for much more customizable options, it is better to use a command line at this point, but we are continuously refining it. So as I said, from the user point of view, what we have to do is setting the experiment config, and rest all is taken care by the Captive controller. The important sections that has to be filled would be, one is the namespace where the experiment has to be run. The next section is the common set of parameters. One is the parallel trial count, which basically says how many number of concurrent trials have to be run. So based on your resources, you could set higher number of trials to be run concurrently. The other one is the max trial count, which is a budget, saying this is the maximum number of trials which would be run during the experiment life cycle. The third one is the max failed trial count, which says maximum number of failed trials that I can have during the entire life cycle. The next is the objective, which says what is my type, whether I have to maximize or minimize. The objective metric name is the metric that I have to optimize, and the goal is the value that I have to reach. So this actually means I have to maximize validation accuracy to 99%. And I can actually provide additional metric names if I want to collect extra metrics during the process. The next section is the algorithm section, where I can specify the list of algorithms. Some are already provided. You could actually add during a development process. I could add extra algorithm settings, which would be taken by the algorithm. And the next section is the parameter section, where, as I've told, this is a place where you specify the search space. For each parameter, I have to basically say the max and min value, or if it is categorical, I can basically say the list of options that are valid for it. And the last option is the trial spec, which is the most important one, which would be where you would be specifying what is the actual job that I have to run. So this is like the one run that we have run using the Bayesian optimization. So you could see that the final results have come to 99%, converged to that. And for each the trial, we can see that what are the parameter values that have given to that result. And you could basically say which one, and you can even go backwards and figure out what are the best values that I have to use it. Yeah, I think.
So a little bit more about this experiment. So this was conducted using about 100 different trials, and this is using Bayesian optimization. So this is one of the most common algorithms for hyperparameter tuning. The idea is like the previous results of the trials are used to optimize the future results. So given that we have selected some parameter values that have led to a good result, we want to improve upon our current status. So if you, it's kind of hard to see from this picture, but if you look at the corner there, we started with maybe about 96% accuracy, and we were able to improve to 98, 99%. So, and if you click on each of these trials, you can actually see how the trial progress over time. So the blue line there is the accuracy that has improved, and there's also the validation accuracy. So in this case, we use the validation accuracy as the objective metric. So we use that to determine how good our current set of parameters is. And there, as John mentioned before, there are also ways to collect other metrics. So we can also see how it correlates with, for example, just the accuracy. Okay, so I want to bring us back to a broader landscape. So, and this is a problem with classical versus automated machine learning. So in classical machine learning, a human expert gets involved in a lot of steps, like selecting features, choosing algorithms, configuring hyperparameter values, evaluating performance, tuning models, right? And a general trend that we've seen in computing is that more and more tasks become automated and more become dedicated to machines rather than having a human getting involved in every step. So, and this is why we have this research field of automated machine learning, which is having a program generating the model without human intervention to reduce all of these time-consuming steps. So what we've seen is hyperparameter optimization. But in the general landscape, There are also other areas like feature engineering and architecture search. So, and I've included a link to a list of AutoML papers, and this is available on GitHub, and it's very interesting. So there's something in common with all of these research, right? So in all the cases, we're dealing with automatically generating a configuration space. So that can include features, hyperparameters, architecture. And in all of these, we generate some kind of a matrix to judge their performance. And based on that, our optimizer algorithm generates a new configuration. Okay. And the output of this is a model which we can use to serve predictions. So in the recent development, we have expanded KATIB to handle neural architecture search. So this is in contrast to the hyperparameter optimization problem that we just mentioned. And the difference is in hyperparameter search, we're only generating values for a list of parameters. So you can think of this as a vector search. And neural architecture search is a graph search. So the space is exponentially higher than that of, is one dimension higher. Right? And there are a lot of research in neural architecture search. So there could be searching for an optimal network, or it could be searching for an optimal cell from which the rest of the graph is generated. And there are also various evolution strategies, such as by generation or by modification. Okay. So the workflow for architecture search is similar to hyperparameter tuning, except that we still have our objective conditions, like whether we have reached our objective condition or whether we have exceeded our search budget. But we've also included constructing a model, because in NNS, the human is no longer, the human expert is no longer providing the model, right? So what we do is the suggestion will generate a list of evolve operations, and from that, we'll generate the next version of the model. And then similar to hyperparameter tuning, we will run these trials based on the model that we've constructed and use metrics to using reporting metrics. We can just judge their performance and come up with the next suggestion for the architecture. So currently we are supporting EnvelopeNet and reinforcement learning for NNS. Okay, so we have seen what KATIB has been able to do for now, but what's coming in the future? So first of all, we want to provide better productionization support. In the architecture diagram, you may remember there's a component for data storage. This is useful because sometimes you want to store your metrics for the next run, or maybe to resume the experiments, or maybe just as backup. But currently, KATIB requires an instance of MySQL to run as the data storage backend. So one thing we want to do is to support customizable database. Another thing is metadata integration. This is in broader scope, and this is a part of the broader Kubeflow team effort. So what we want to do is suppose that you've done some hyperparameter tuning experiments and you're able to produce some pretty good results, right? So you want to take those models that you train and serve them, right? So this requires some kind of a generic store where you can store your metadata and to be used by other parts of your machine learning pipeline. Finally, we have supports for other features like long-running experiments. So suppose you have tried to some combination of parameters, but you want to change your algorithm a little bit, maybe change your budget, and you want to continue experiments from before. So this will provide better support for a hyperparameter service in production. Another aspect is that we want to add more features relevant to automated machine learning, such as model compression and automated feature engineering. So we've seen how Kaggle can deal with hyperparameters and neural architecture search, right? But that has to do with the training process. The feature engineering will be the step before all of this begins. Right? You're selecting your list of features. Maybe you're doing some kind of feature selection, or maybe some feature process, or maybe some transformation, right? To transform your training data. And so these are the things that we're constantly researching. Okay, so how do you contribute? So you can find us on GitHub, and there will be, feel free to submit feedback, try our service, and provide feedback and feature requests. There will be lots of help wanted features. And a great way to contribute would be to help with the infrastructure and testing improvements, and maybe adding some new algorithms. So currently we support maybe 5 or 6 different algorithms. So, and our intention is for Kaggle to evolve into this open source platform for the generic automated machine learning, right? So we would really welcome contributions. And there's an invitation to our Slack channel. You cannot open it from here, but it's if you're interested. Okay, finally, we want to thank a lot of our contributors. Some are in the audience today. So NTT, GuideCloud, IBM, Cisco have always been very, very helpful. Okay, so that is it for our presentation, and we will take some questions. Yes?
The DB backend that this has, Native has, how pluggable is it? Like how can you change Can you change the DB backend from the current implementation to something else?
Yeah. So currently in V1 Alpha 2, which is the version which is coming in a month, so that's not possible. But in the 0.3, the next version, it will have a pluggable version where you could add any database and you could just implement the common interface.
So the question is about the consumption of resources and so the question is about the consumption of resources, right? So resource you can configure on a per job level, right? So there are a few ways to configure how much of resource you want to consume. So one way is for your budget, right? So if you want to have a smaller parallel budget, you can adjust how many trials you want to run in parallel, right? And another way is to change the specifications on the training job. So some training jobs you can use multiple GPUs. Maybe some you can reduce the number of GPUs. Right. Okay, so the question is, do we still need machine learning experts after we have neural architecture search? So I think a lot of research is going into how to efficiently generate neural architecture search, right? So it's not, so a lot of this is still very early, right? So we're still researching into how to efficiently generate, how to generate not only within the limited budget, but also make it applicable to various kind of problems. So I think currently neural architecture search is pretty good with image recognition, but there's a limited application elsewhere. So this is still something that still requires research.
Thanks for the presentation. So I have a question for for this slides, do you have a simple use case that the Cative can show that Cative can maybe in which stage that a machine learning programmer can use it? For example, I wrote a simple training program and I got the some model, but I don't satisfy with it, and so what's the Euro cases that this Cative project can fit in? So I think I'm not quite clear of this question, this problem. Maybe a typical use case is.
Yeah, so as he described earlier, the wrong settings would actually have very bad performance of the model, right? So for example, in the demo slide that he showed, if he so here, if you see that for certain parameters, you could see that the final accuracy has come to what's the value here? Just 11%. So it actually depends on how do you actually figure out what's the best hyperparameter values for your experiment, right? So here, the clean advantage that you actually get is you don't need to worry about setting the hyperparameters. You basically get the best hyperparameters that is suited for your model. So as he described earlier, the model performance continually improves, and finally it gets to 98% in this case.
Okay, thanks.
Yeah, I have a very general question for Richard. So from Google's perspective, is Kubeflow driven by Google AI or Google Cloud?
Your question is about whether the
Yeah,
Kubeflow product.
Yeah, internal Google, who is driving Kubeflow project? Is Google Cloud or Google AI?
So it is the Kubeflow organization is under the Cloud AI organization. So the team that's driving it is Google Cloud.
Google Cloud.
Right.
Yeah, so I kind of have a feeling that from Google AI, for example, TensorFlow is very hot in the AI domain, but looks like Kubeflow is not that popular at this moment. Maybe I'm wrong, so maybe you can give me more insight about that.
So our goal is to democratize AI, as not just targeting TensorFlow. Right? So we want to make it easy for people to build end-to-end machine learning workflows on Kubernetes, on the cloud. So that's why the Cative and other frameworks are agnostic to the framework.
Okay, I see. Okay, thank you.
我对那个自动 automatic 我对那个 automatic machine learning 有一个小问题，就是我们通过神经网络搜索出来的那个，就传统的特征工程，我们